Looking at non-existence. If you want to know what existence is, why it exists, and how it works, the first and most rational thing to do is to look for an example of existence coming into existence. You will not find that by looking at existence. You must look at non-existence, and the closest thing to non-existence you would find is a vacuum. When you take every particle out of a confined space, you're left with a three-dimensional nothingness, a vacuum. To understand a sphere, it's useful to first try to understand a circle. Apply the same logic. To understand a three-dimensional nothingness, we must first attempt to understand a two-dimensional nothingness. Occam's razor holds true for many significant aspects of reality, and so serves as an obvious place to start when trying to understand anything. Yet scientists formulate the most complicated equations to attempt to understand the origin of existence, which is arguably the most significant phenomenon of all, and so probably has the most deceptively simple explanation. So let's start from the beginning and use Occam's razor. A fabric of nothing. To understand a fabric of nothingness, it will be useful to first understand a fabric of somethingness. Imagine you've got a football field-sized piece of cardboard. You lift up one end and pull it back down again quickly. It requires a lot of effort and creates a rather rigid wave. Replace the cardboard with denim and it requires less effort and produces better waves. Replace the denim with cotton and it requires even less effort and produces even better waves. Replace the cotton with silk and this fabric becomes almost effortlessly wavy. Notice that we started with a thick fabric that we replaced with thinner and thinner fabrics, each requiring less and less effort to produce better and better waves. This gradient should continue infinitely until you've reached the fabric of nothing, which will require zero effort to fluctuate, meaning it will fluctuate spontaneously by default, non-deterministically, and it will allow for perfect waves. This is what physics calls Heisenberg's uncertainty principle. But to demystify it, it is just pure mathematics incarnate, the purest possible form of 0 equaling 1 minus 1. And remember, this fabric is not two-dimensional, but three-dimensional, so those fluctuations should look something like the blobs in a lava lamp, peaks and dips, positive and negative regions, always adding up to 0. But there's an even deeper way to arrive here. In the beginning, there wasn't just nothing, there wasn't even space, there weren't even three dimensions. You could have 0 dimensions, the 0th dimension. Even though there is no dimension of time, it is a timeless, dimensionless fact that exists across all dimensions, including dimension 0, that 0 equals 0. But 0 also equals 0 plus 0. Think of the 0th dimension as being an infinitesimally small point, and then take it to the end, even smaller. The smallest possible point, with no depth, no width, no height, no charge, no vibration, nothing. There is no space. There is no space for there to be nothing in. Nothing that we have ever been able to talk about, or comprehend, or think about was possible. And in that moment, that point became 2 points, simply because 0 equals 0 plus 0, and that gave us the first dimension, a line. Then it can happen again, and now it was no longer just the first dimension, but the second. If you were to draw lines between them, you'd be able to create a triangular plane with a thickness of actual 0. Then obviously it can happen again, and you've got 3 dimensions. But as we know, 0 can equal infinite zeros. And so, because of this absolute fact of mathematics, and because there is no time, time is something that only exists for particles, and we're not talking about particles yet, we're talking about just 0, that 0 instantaneously multiplies by infinity, resulting in an infinitely large nothingness made up of infinite smallest quanta of nothing, an infinitely large void of space. But then, because 0 can equal 0 and 0 can also equal 1 minus 1, that space doesn't just stay flat. Instead, it fluctuates, positive and negative. These are vacuum fluctuations. From fluctuations to particles. If such a phenomenon exists, it would be expected that the positive and negative fluctuations within a vacuum would always add up to 0, but would move around randomly. From time to time, 2 negative dips and 2 positive peaks should overlap side by side, strengthening each other and becoming what we can only intuitively assume to be the powered-up version of fluctuations, vibrations. These vibrations are what I interpret as the basis of virtual particle pairs, positive and negative counterparts briefly appearing together, such as the electron and positron. On larger scales, many peaks and dips may overlap at once, giving rise to many such pairs. In essence, each pair would emerge with opposite charge, opposite momentum, opposite spin, and opposite directional tendencies, so that the total system remains balanced. Their appearance is not arbitrary, it is governed by an exact conservation relation. They borrow from one another and must, in the end, return that balance. To test whether anything like this is really happening, we look to the vacuum experimentally. We shine light through it, we place plates around it, and in experiment after experiment, we find signs that empty space is not truly empty. Tiny disturbances, measurable effects, and evidence consistent with transient particle activity. That makes the vacuum our strongest empirical clue for how something can arise, briefly and lawfully, from what otherwise appears to be nothing. On this view, reality is not merely governed by mathematics. Reality is a three-dimensional fabric of nothingness behaving mathematically. Creation itself is mathematical behavior embodied. The next question is scale. If there were infinite space fluctuating across infinite time, what is the limit of how many peaks and dips might eventually overlap side by side? In principle, there is no limit. Given enough room and enough duration, ever larger concentrations of balanced positive and negative activity should emerge. What begins as brief, local particle pairing may, at the limit, become an effectively boundless outpouring of matter and antimatter. That is the threshold at which the argument moves from vacuum physics into cosmology. Black holes and white holes. In 1916, Einstein's general relativity described gravity as the curvature of spacetime by mass and energy. Among its solutions are objects so dense that nothing can escape them, black holes. The Schwarzschild solution describes the geometry around a spherical, non-rotating, uncharged mass m. ds squared equals open parenthesis 1 minus 2 over gmc squared r close parenthesis c squared dt squared minus open parenthesis 1 minus 2 gmc squared r close parenthesis to the power of minus 1 dr squared minus r squared d omega squared, where minus ds is the spacetime interval, minus g is the gravitational constant, minus m is the mass of the object, minus c is the speed of light, minus r is the radial coordinate, minus d omega is the solid angle element. When r falls below the Schwarzschild radius, 2gm over c squared, spacetime becomes so curved that nothing, not even light, can escape. The equations also permit a time-reversed solution, the theoretical opposite of a black hole, a white hole, from which matter and light may only emerge. ds squared equals 1 minus 2 over gmc squared r to the power of minus 1 c squared dt squared minus 1 minus 2 over gmc squared r dr squared minus r squared d omega squared. For a long time, white holes were treated as mathematical curiosities, but the vacuum-based picture developed here appears to point toward a strikingly similar phenomenon from an entirely different direction. If these two pictures are tracking the same underlying reality, then one implication follows immediately. If black holes converge and merge, white holes should diverge and separate. And if a white hole were born at effectively infinite scale, its separation would also be effectively instantaneous. There is also a structural reason for that division. If the vacuum is required to produce an immense quantity of particles, and a single outlet is not wide enough to release them fast enough at the first instant, then that outlet must split. One white hole becomes many because the system must open wide enough to release the required flood of matter immediately. The chaos of creation. Each of those white holes would then eject an incomprehensibly large quantity of particle pairs into an extraordinarily hot and dense state. At that point, the system would behave less like neatly separated particles and more like one enormous turbulent field of collisions, transformations, mergers, and annihilations. This is why the earliest universe should not be pictured as finished matter and finished antimatter standing cleanly opposite one another. It should be pictured as a chaos of interacting components, constantly breaking down and recombining. A simple analogy helps. Imagine 50 red marbles and 50 blue marbles smashed together so violently that some crack, some fuse, and some become altogether different kinds of marbles. In principle, you expect rough symmetry, but not perfect symmetry in every local outcome. 24 blue marbles may break while 26 red marbles do. The larger the chaos, the more inevitable it becomes that slight asymmetries appear. On this view, that is how a matter-dominated universe can emerge from a fundamentally balanced beginning. Some of the particles that would have balanced our matter by becoming antiprotons instead transform into lighter particles, such as electrons and neutrinos. The asymmetry is not intentional design. It is statistical inevitability inside an immense and turbulent creation event. From there, electrons rejoin protons, hydrogen and helium form, stars ignite, heavier elements are forged, supernovae scatter them outward, and eventually planets, chemistry, life, minds, and intelligence emerge from the same original balance-breaking process. Dark energy. Black holes draw space-time inward. White holes, on this view, would push space-time outward. And because a white hole expels rather than retains mass, there would be no enduring dense body left at its center to behave like an ordinary visible object. That raises a question. How would such entities be detected? The answer may be through the large-scale expansion of the universe itself. If white holes warp space-time outward, then surrounding galaxies should be driven away from one another. What we call dark energy may, in this picture, be the large-scale signature of white holes repelling spacetime from within the cosmic voids. Locating white holes. If white holes have negative gravitational behavior relative to galaxies, then they should drift away from regions dense with matter. The most likely places to look for them would therefore be the deepest voids between galaxies. Geometrically, one way to model this would be to map galaxies into three-dimensional networks, connect them into large simplices, and look for the centers of the voids defined between them. Those central regions would be the natural candidates for white hole locations. Dark matter. A universe driven partly by white holes would also imply something else. If outward gravitational effects are acting from beyond galaxies, then the motion of stars within galaxies may look as though there is more inward gravitational pull than visible matter alone can explain. What we currently call dark matter may therefore be, in this framework, not hidden mass inside galaxies, but the dynamical effect of negative gravitational structures outside them. The discrepancy remains real, the interpretation changes. Unifying quantum mechanics and general relativity. General relativity is often illustrated with the image of a bowling ball deforming a rubber sheet. Useful as that analogy is, it makes it difficult to see how quantum behavior might connect to gravitational curvature. A better image is a bedsheet. Draw a straight line across it to represent Earth's inertial path. Then pinch the sheet at a small point elsewhere to represent a particle locally vibrating space inward. The effect on the line is minimal, but if, where the sun would be, you pinch a great many such points together, the surrounding geometry bends in a way that curves Earth's path. On this picture, gravitation is not separate from the microscopic behavior of particles. It is the large-scale geometric consequence of many local vibrational distortions within the fabric of space itself. The double-slit experiment. The same framework also suggests a way of thinking about the double-slit experiment. Vacuum fluctuations may pass through both slits, creating an interference structure in the field itself, and that structure may then guide the path of electrons or photons through a pilot wave-like effect. How the universe will probably end. Black holes have a birth and a death. They are formed through collapse and, over unimaginable timescales, evaporate through Hawking radiation. If white holes are their opposites, then they too should have a birth and a death. If white holes are what drive cosmic expansion, then the death of white holes would mark the end of that expansion. At that stage, the radiation and matter distributed across the universe would begin, however slowly, to return toward one another. But by then, the waves associated with those particles may be stretched to extraordinary scales, galactic, intergalactic, perhaps cosmological. When they finally meet again, they may do so with so little usable energy that they cancel perfectly rather than interact turbulently. The long equation resolves back into its simplest form. Everything returns to balance. Everything returns to zero. What this resolves. On this theory, the same underlying structure would explain the origin of the universe, the apparent effects of dark matter, and the apparent effects of dark energy. In other words, the three largest open problems in contemporary cosmology may not be separate mysteries at all, but different expressions of one deeper principle. Meaning, if this picture is right, then the universe did not create life intentionally. It created life inevitably.
Hey YouTube, that was my video essay. I just wanted to say thank you so much for watching till the end. Like and subscribe, stay tuned, help me go viral. Yeah. See you in the next one.